So our second speaker is coming to us from the University of Texas at Austin. And so that's Professor Yuke Zhu, who is an associate professor in computer science and also a distinguished research scientist at NVIDIA Research. And so he'll talk to us about his work on building foundation models for humanoid robots. Okay, Yuke.
For the introduction, I'm honored to be here. So I really enjoyed the talk given by the scientists, from different disciplines. I'm more coming from the AI end of the spectrum, right? So the talk will be a little bit different, as the title suggested, that I will talk about humanoid robotics. But I do believe that science and scientific discovery is one of the most impactful application domains for this robotic automation technologies. So I will share a little bit about our recent progress in building generalist robot, but also the challenges. And then I want to conclude with some of the potential opportunities, how we can collaborate together between the robotics researchers and the scientists to advance science. Okay, so to start, maybe I will just through a pop quiz of a history of science and really quick, who invented the steam engine? Anybody? Yeah, there. James Watt. Yeah, great. Yeah, so when I ask this question to my students, and always so this person is a Scottish gentleman that is the most popular answer, right? So indeed, James Watt is the most recognizable name when we think about the steam engine. It's actually on my high school physics, a history book, exactly this picture. But some of you might have a better answer that not a single person, right? So if you look at the evolution of steam-powered machines, it's really a gradual process throughout a long period of history. And to confirm this, I asked ChatGPT, right? So as we usually do. So it also says well, the invention of a steam engine was a gradual process and involving some key figures, and over time that you see the last name is James Watt, right? So and then, but it also says well, James Watt is credited with inventing steam engine, but it really is a long continual process. When it comes to science and technology, we're all standing up on the shoulder of giants. So the reason that I actually, if you look at the history a bit, the very first account of a steam engine comes in Roman Egypt, right, in the 1st century, and throughout the century, multiple hundreds of years, so people come up with different variants of those, and all the ways to the modern kind of energy solutions, right? So, but in the earlier version of a steam engine, so they are really kind of purpose-built prototype that only work in very limited conditions. The times goes to 1763, I think, that James Watt makes some important improvement over previous design. It's actually based on Tom Newcomen's atmospheric engine. So if we look at the innovation itself, by no means it's really revolutionary, right? So if we are writing a paper about it, the reviewer too might give a big reject. But what's important about it is that it's just practical enough to reach the widespread adoptions. It's good enough for solving real-world problems. So people start to put it in locomotive, in factories, in cars, right? So, so in automobiles. So, and in fact, James Watt's innovation on steam engine become the hallmark of first industrial evolution, right? So, and the people start to kind of apply this to different domains that kind of leads to new industries and new problems to solve. But now we are seeing, by no means we're going to find the OG steam engines in the modern energy solutions, and we come up much better ones like internal combustion engines, thermal turbines, right? Because that kind of revolution in energy solutions are driven by initial James Watt's innovation really kind of deepens our understanding of the potential of different energy sources that leads to more customized solutions that kind of have their unique strengths and different problem domains. So the reason that I talk about the steam engine a bit is because history tends to repeat itself, right? And we see this recurring patterns in the neighboring field of AI going from a specialist solutions to some generalist approach that leads to widespread adoption, and then we build on top of this general solution to build a better specialist. So if you look at natural language processing, and it kind of follows the same trend in the past couple of years, right? So the earlier NLP model focused on specific language processing tasks. You can have a semantic parser, parse language into English sentence into tree structures, analyze their sentiments, extract key information, or summarize a long paragraph into short amount of text. But what ChatGPT and the recent language model shows that we can actually centralize training to one artifact, and people call it the foundation models. And this model are not jack of all trades, master of none, right? So they actually have trained on massive amount of text data so that they can encode a lot of knowledge about human language and word common sense knowledge, so that we can use that to build a lot of downstream applications. So we can use this language model to write like poems, like a Japanese haiku, like much better than I do. You can use it as a coding pilot to write source code for you, give travel suggestions. If you think about writing any of this specific natural language task from scratch, it's incredibly hard. But by having this big base model, right, so it makes the downstream task a lot easier. So now let's turn our eyes to robotics. I think so. In the past, a couple of decades, I think the robotic community collectively had made a lot of progress in building very specialized robotic systems. Sung Jun showed some of the impressive videos of robots achieving human level, some superhuman level performance in some specialized tasks. But we're still far from the kind of dream of building generalist robots that can deploy to everyday household and environments, right? So I argue that to be able to get there, one of the key to build this kind of generalist robot model, similar to the trend of large language model, that they should have a set of core competencies, but in the meantime, they should always learning to acquire new skills in new domains. So that's kind of our goal of a lot of our research in the lab. And so as a robotics group, we have been working on a variety of robotic platforms in the past, starting from robot dogs, quadrupeds, to quadcopters, and to tabletop arms. Very recently, we kind of converge on this unified platform of humanoid robots. And so why humanoids? And these are the robots that have 2 legs, 2 arms, and 5-finger hands, right? So that makes it very suitable to be integrated into the human world. So there's definitely business reason to make why we make humanoid. Suddenly, this become a thing that's captivated the industry and academia so much in recent years. But as a researchers and as a scientist, there's a couple of argument to make why we work on humanoids. This is not saying of course there's a lot of roles and to play in those specialist systems that I showed you earlier. But because we are working on robotics as a physical system, at the end of the day, the hardware embodiment determines their capability envelope, right? So if you work on robot dog, at best we can get dog level intelligence, which is very impressive on its own, right? But if you want to work on so-called human level physical AGIs, right? So you need a physical body that's versatile enough to perform the kind of wide range of tasks in the natural world. The second is now is actually a better time to work on this robot because the cost has dramatically decreased over the past 2 decades, right? So from the NASA robot analysis, really custom built one-of-kind robot that price at 1 million North, to nowadays you can buy a robot as a price of a car and order it online, ship it to your home, right? So the next day. So it's really becoming a kind of commercially viable products. And not only they are cheap robots, they're actually very capable robot as well. Right? So this is showing this a $50K unitary robot. Because I'm in LA, so I want to show tributes to LeBron James and Kobe Bryant on this kind of athletic movement with this robot trained with reinforcement learning. The third is we call humanoid as a brownfield project because so we human build our worlds for our embodiment, for our form factors, similar to the lab environments or factories. It doesn't make sense to tear down this environment and build new ones and completely customize to the robot. It's so much easier if we can just build a robot that follow our form factor and roll into this existing environments. And the last, as a technologist and as an AI person, right, I think there's a technical reason to make why we build humanoids is because that unlike the other areas of artificial intelligence, such as natural language processing and computer vision, there's a huge amount of data from the internet. There's not an internet of robotic control, right? So you cannot download robotic data without the action labels from the internet. So we kind of need to be creative in finding the training data, the data source to build the AI models. but because they share similar physics, that kind of unlock a lot of like a human-centered data, like from the motion capture database and created by Hollywood to all the YouTube videos and TikTok video of showing human doing everyday activities. Right? So potentially with that kind of closer embodiment, we can tap into this data source for learning. So now I kind of like pick humanoids as an embodiment. Like, so what would be the way to scaffold their autonomy? What's the AI model will be like? A lot of our research, I think, are kind of inspired by discoveries in, like, say, cognitive science and neuroscience, and I think, like, so, especially so Daniel Kahneman's dual system theory, right? Kind of characterizes two thinking system of a human thinking patterns. Like, I think that idea is already kind of popularized by the book Thinking Slow and Fast, right? So, well, it says like, so there are also this two system, system 1 and system 2. System 1 is they call it fast brain, that is unconscious, intuitive, and reactive in your body. You can think about it as a low-level sensor motor control. You have to react to the here and now, right? And then you have a slow thinking system, system 2, that is conscious, deliberate, and effortful. In your body, you can think about it as a high-level cognitive planning and reasoning, like think about like so breaking down a very complex task into subtasks so that you can develop and conquer, right? So inspired by this kind of a dual system theory, and we architect our model to have that kind of a two-system design. You have a system 2 model, which is a big brain with billions of parameters. This is the vision language model that processes the language instruction and the image input to the model, and then does some kind of processing and reasoning to generate some latent thinking tokens. And this kind of latent thinking tokens can be passed to a much smaller system 1 model. This is usually tens or hundreds of million parameters to generate a high frequency motor control at a 30 to 50 hertz so that you can run on board for closed loop reactions. So this is a model that we published earlier this year called GR10-1 that is open source, and you can try yourself and on GitHub. So with this architecture, and we train on massive data sets, like the pre-trained model that trained on massive multitask data already have a good amount of generalization capability. It can follow language commands and to pick up objects and in different conditions. But it can also post-train, meaning that you can collect some task-specific data in small amount, and then like fine-tune the model to adapt to some downstream specific tasks, right? So this is showing that so the two robots running two GR models side by side to perform this kind of industry assembly line tasks. So that's the architecture. When we are talking about the kind of a recent progress in AI, I think it's really driven by the trinity of three key elements. One is compute. We have like accelerated computing platform like GPUs. We have like advancing AI models like transformer architectures. But the third, equally important, is the data sources, right? As I already said earlier, that so for robotics, the challenge of building foundation model is that we don't have as large data sets as the internet to train for vision language model and LLMs. So rather than kind of like trying to scale the real robot data only, like so, about 3 years ago, I introduced this concept called data pyramid. It was a very pragmatic approach. I was just looking around to see what are the data that's potentially available and valuable for training our robotic model. And then I organized them by size and into their 3 tiers, right? So on the top tier is real robot data. So these are the things that you can get from real robot physical hardware. Right? So they are the highest quality data, you might argue, because they come from real-world sensor, real-world motors. If you train on this data, there's no reality gap, no domain gap. You can directly deploy the model back to the real hardware. But the catch of this is like, so for each of the robot, you can generate at most 24 hours of data per day, right? So we are really bounded by reality here. And then the second tier is simulation and synthetic data. I see in many talks like people are using simulation for science, different scientific domain as well. So you can argue that so well with infinite compute, with I can just let the simulation run to generate a massive amount of simulation data. But the challenge of using simulation is like so creating those simulations is still a very tedious and manual process. Right, and also, like, so if your simulation is low quality, it's going to be garbage in, garbage out. So it actually hurts the model performance if you get like so not high quality action data. And the last is like the human video data. These are just the passive observation of human activity. We don't have the human actions labeled with these videos. But the nice thing about it, there's a tons of them. Right? So the human society collectively contributes exabytes of human data per day. And that's an astronomical number. That's millions of terabytes of data per day that is very human-centered. Potentially, we can use that data for training. So rather than pick favorites, like so a lot of our research looks into how do we actually kind of leverage all these data sources combined. On the top tier of the pyramid, I show you the real robot data. This is like real data is still important so that we don't detach from reality, right? So at the end of the day, the robot models need to see some real data to stay grounded. But you can see already see this is a very costly operation, right? So this is like a time lapse of like our labs collecting real robot data through teleoperation. Usually for one robot, you need 2 or 3 people working together for teleoperating, resetting the environment, and labeling the task, right? It's a very tedious and a manual process. So it's and fundamentally, it doesn't scale because the amount of data you can collect is only linear with respect to the amount of time and the money you put in. So rather than relying on simulation data only, real robot data only, so we've been looking into simulation as a way to really scale our training data, right? So the nice thing about simulation is once the simulation is built, you can vary different axes of a variation, changing the lighting, changing the object, changing the textures. So you can get from linear data to exponential data, right? So when it comes to training data, we like those exponentials. But challenge of simulation is that in the past, like usually this kind of simulators requires graphics designers and simulation engine experts to carefully orchestrate the simulation so that like to set up the things so that we can start generating data. So there's a premium to pay, right? So to leverage simulation. What really changed the equation is the availability of generative AI tools. Now we have much better AI tools to create simulation environments. To give you an example, this is one of the recent research work called RobotCasa that we leverage a bunch of like a AI foundation model to create a realistic simulation environments. For example, we use a text to 3D model to create all the 3D assets. We use a large language model to write the reward function and task objectives. And we use an image generation model to randomize the textures, right? So they really give you the kind of vast amount of variety of things and for free, right? You leverage compute and the AI models. After we have this simulation environment, we also develop another system to generate trajectories in this synthetic simulation environments. The idea is that we can still use teleoperation to collect a handful of demonstrations for each of the simulation, and then we let the compute do the work, right? So we use compute to replace the human time. And then the idea here is that we can run simulations to transform the trajectories and that we collect from the source demonstrations to the targeting environment using some functional equivariance, right? So we can like morph the trajectories towards a new object initialization in the new simulation so that we can kind of multiply the trajectories from a handful to thousands of trajectories to give rise to a large data set. Okay, so now what I talk about is one way of generating synthetic data, right? That is leveraging physics simulation and traditional graphics rendering. And recently, there's some exciting development in artificial intelligence. That is, people have been looking at the neural network as a way to scaffold the backbone for word models. And in particular, people have been looking at ways to train video generation model that will take one picture or language prompt as input, and then imagine how the future will look like. And half jokingly, that community has been using this test, Will Smith eating spaghetti, as a way to assess the model capability. And you see that so over the past 2 years, there's a tremendous progress in this type of like word models, right? So this video showing on the left is how it's like 2 years ago. You see that Will Smith sometimes eating spaghetti with a hand. There's no really temporal consistency. Sometimes it shows a different person, right? So that's kind of like what the state-of-art model looks like in 2023. And this is one of the new models coming up like earlier this year from Google called View 3. So you see like so the consistency and then the motion is getting a lot better and over the 2-year period. So things are moving really fast like when it comes to like so the word model building. So because of that, like so we've been looking at ways of leveraging this video generation model as another way to do like synthetic data generation, right? So you can take a image observation and language instruction as input, run the word model to simulate how the future looks like. And then you can also use another model, like a vision language model, to check whether this follows a language command and remove the bad example that does not necessarily match the language prompt. So we call this a dream gen because like so it's kind of dreaming in that kind of a video generation model. But one difference of this type of generative video compared to the mimic train pipeline is that we don't have action labels, right? So all we have is just a generated video sequences. So we need to train another inverse dynamics model to label the missing actions from the adjacent video frame so that we can turn that into a neural trajectory that we can leverage for the model training. So these are the kind of ideas like how we leverage this new model for video generation. And then I would say that so there's really pros and cons between the kind of more classical physics engine-based generation versus like this type of neural generation. For certain physical phenomena, such as pouring water, deal with like fire, is super hard to simulate in the traditional physics engine. Right? So you can imagine like so building some finite element models, having really complex ODEs, and to be able to simulate those kind of physical phenomena. But with this neural network approach, it's constant runtime. Like so, no matter what kind of physics you want to simulate, like so, you just run the inference and with constant compute and to be able to simulate. So now we have this 3 different type of data sources, as I mentioned. One is a robotic teleoperation that we can have a human, like so, remote control the robot to collect such data. But the thing is, like, they are quite costly, time-consuming, so we only get them in small scale. We have things that are coming from a physics engine. You can see like so they sometimes have like rendering and gaps. But the nice thing is like so because the physics engine are written with some physics first principle, right? So the actions are actually high quality because they are derived from the physics equations underlying. And then the third source of data called neural trajectories are coming from video generation model. They look as realistic as the real robot teleoperation data, and then they can simulate very complex physics phenomena. But the challenge of this is like so you don't have action labels, so the action are actually predicted by another AI model, so that can be a bit noisy. So given the kind of complementary strengths of these 3 models and how do we use them, so we come up with like yet a simple and effective approach, which is called co-training. Well, the idea is quite simple, that you just sample data sets from all these 3 mixture data sets, but with some load balancing because like they come in different size and different quantity, different characteristics. You need to kind of balance out so that they have like so equal influence to the model training. And then we sample mini batch and do the standard like SDG, stochastic gradient descent loop, like so to train the model until convergence. This has been quite effective. Quantitatively, we show like so by adding the simulated trajectory and neural trajectories to our real robot data sets, both contribute positively. But if you can mix both, and that leads to the highest model performance in our manipulation tasks. I want to highlight that like so the idea of a co-training has been recently getting popularized like in the field of robotics, and people have been exploring this as a core technique to train across mixed data sets. Like so we have done semi-real co-training, but there's also other works that explore like so how to co-train between human data and robotic data, as well as like so data that come with action label versus like actionless video data. So that kind of like and also of course like so the co-training was not really a new idea. It's really kind of based on pioneer work in machine learning, like the semi-supervised learning and domain adaptation. So that kind of like motivates us to understand better why co-training works, right? So so the way that we examine that is by looking at the representation learned by the co-trained policy, and then what are the kind of representation emerge in the kind of simulation samples versus real world samples. So these are the visualization from the intermediate layer, from the visual encoders and of the trained policy. You see that you start to see that some interesting patterns, right? So the blue set and the red sets, which correspond to the real and the sim sample, they kind of share similar shapes, right? So when we project that down to a three-dimensional space, and this is not a cherry-picked result, and we actually kind of look at the sim for a variety of tasks, and the observation is consistent. And this also gets confirmed quantitatively, and we can calculate this Gromov Wasserstein distance, and which measures the intrinsic structure similarity between two feature sets. And then we see that the co-trained policy has much lower GW distance compared to the one that's not co-trained.
To ask you a question about that video. So as a humanoid robot expert, do you think that it's really a good application of human robot? For example, it looks like a library, quiet room, and when that humanoid robot walks, it actually makes sound. And I kind of see that maybe you can just completely replace that robot with a wheeled robot. Yes, it's fun to have a robot throwing an apple. You can actually have a robotic manipulator still. So you can still do the same thing, a lot safer, even more quietly, and maybe faster.
Yeah.
So what do you think?
Well, I think so. You're right. So in a lot of domains, so if you have flat a factory grounds, so those kind of office settings, a wheelbase can go a long way, right? So and actually having a bipedal platform is a non-stationary platform. You always need to maintain balance while physically interacting with it. That definitely makes the problem harder. But in a lot of domains, so I think having the bipedal platform does benefit. I'm looking at this an auditorium. We have stairs and so when I was actually visiting Japan last year, they show me the small Japanese homes and with all the stairs and the narrow corridors, and for those type of deployment environment, it would be really difficult to have a large wheelbase, and so as navigating uneven terrains in kind of unknown environment. If you I see the picture of show the picture of DARPA Robotics Challenge. That's actually inspired by Fukushima nuclear disasters, right? So if you go to the nuclear disaster site, it'll be really difficult to deploy a wheel platform. So for those are use cases I think you need lax. But if there's a particular problem, more kind of a specific domain to solve, I think a wheeled platform goes a long way. Yeah.
I think we have one question.
Yeah, this is a great talk. It was very inspiring to see all the work being done in foundation models and humanoids. My question is, I think the justification, the motivation for humanoid robotics specifically is very clear. But I'm curious on the other form factors of robots, so like autonomous cars, you have UAVs, you have spacecraft. You can name many different things as autonomous systems. So what are your thoughts on applying foundational models in those domains, and what is the motivation behind them?
Yeah, as I said, so there's definitely roles to play in. I don't think we'll converge on just only one particular embodiment. Humanoid is nice because a standard platform you can redeploy, and ideally, so the kind of the technology can aggregate over time because you kind of standardize the kind of embodiments. So that's an argument to make, but equally, so there's people working on autonomous driving cars, and it's equally big or even bigger industry. I think also there's challenges on the of building autonomous driving and a humanoid, but the humanoid system is a lot higher degree freedom, right? So, but I think for autonomous driving domains, if you really want to deploy L4 or L5, you do need to solve all the long tail problems, right? So it doesn't make sense for a car to drive in a parking lot environments. But humanoids, there's a lot of value creation if you only focus on very narrow domains in factories, in warehouse, and in the repetitive tasks in lab settings, and you can have a robotic graduate student that does experiment 24/7, right? So in that kind of a small workspace, you don't have to solve all the long tail real-world challenges and to make it useful. So there's kind of a different challenge and pros and cons of those, but definitely there's a values of worth building and working on foundation models for other type of embodiments. Yeah.
One very last, very quick.
A great talk. I was curious about the role of foundation models. Some of the videos you showed are task specific. What's the best way to bridge between task specific learning versus foundation scale learning, where you can ask a model robot to do anything?
Yeah, so what's the role between task specific versus more general learning? What we found is similar to large language model is most of the knowledge accumulation happens in the pre-training phase. which means like, so yeah, really it's the pre-training stage you acquire all the knowledge about like how to understand the word, how to generate like so versatile behavior. And in ideal case is that like, so if your model is pre-trained well, it should encode all the core competencies so that during test time, you can learn very efficiently, right? So the more you pre-train, the stronger the pre-trained model is, the less data you need to collect on the task-specific settings. So that like, so during post-training or that kind of adaptation phase, all you need is to do knowledge expression. That you are expressing the knowledge you encode in the pre-trained model rather than have to learn new tasks and new skills from scratch.
So with that, let's take our speaker one more time.
Thank you.